Hello everyone. So in this session, we are going to start a new topic and we are going to talk about rotation in fluids. And The first thing I want to talk about is what is the difference between vorticity and rotation and how they are related to each other and how we define vorticity and rotation in a fluid. And after that, we are going to use what we call irrotational flows, and then we are going to work through some simplifications again of these governing equations for velocity using velocity potential and stream functions for 2D flows to be able to drive some simple analytical solutions for some of the canonical flows in our course. Okay, so let's get started with vorticity, and let's see how we define vorticity in a fluid. So we call curl of velocity, which is the cross product of grad and velocity vector, the curl of velocity, omega, the vorticity. Okay. So let's investigate how this is related to the rotation of the fluid. So how this is related to the rotation of the fluids, of fluid particles. By the rotation. So let's say we have a rotation. Let me change this to by the rotation vector let's say W or omega. Okay, so in order to answer this question, how is this related to the rotation of the fluid particles by the rotation vector omega? Like, what is the relation between omega and vorticity, or W and this omega here, capital omega? So consider a fluid particle. So in order to answer this, consider a fluid particle. Let me put it here. In a flow with velocity gradient only in the XY plane. So say here is X and Y. And we have this fluid particle, okay? So let's say after dt, like a short interval of time, so in dt, the particle moves and distorts, right? So we want to see how much it is rotated actually. How much is this particle is rotated. So After a short interval dt, let's investigate a scenario, a general scenario that we can have. So for example, we can have the particle could move here. This part, this corner can move here, and then it can also distort and rotate. Okay, so let's see what we have. So it can slightly rotate, like in the other direction. So it can do something like this. Okay, after dt, this can be rotated and moved and be converted to something like this after a short in a time interval. So let's see this corner, we call this O. So we have, first it moves. So this part we know, if we have u of O, u at O in the x direction, this distance is uO times dt after a short interval. And this distance is going to be v naught times dt. Okay. So now we are particularly interested in these rotations here. So these two angles, so first we have these, let's say this much rotation here, which we call it d alpha. And then we have this much rotation here, which we call it d beta. Okay. We also know that this distance is how much we have rotated, right? So we can calculate this. This is going to be partial v over partial x, right? Because this is going upward at O times dx. So this is the additional part of that, right? Because so this part we know is v naught times dt, right? And then this is the additional part. If you write the Taylor's expansion, then this times dt. This is going to be how much we are going to move on the right. Right? So basically, you can get it simply, or you can just think of it if you just write, if you want to get the velocity of here, let's say velocity of here, this point, you can write this in terms of Taylor's expansion as it's going to be v naught plus partial v partial x at O times dx. This is going to give me, let me see, this is going to give me the Taylor expansion is going to be v at, say, at right corner, at right is going to be v at O, left corner, plus partial v over partial x, O dx, and then we have other terms which have like dx squared, etc., which are small, so we can just neglect them compared to this term, which is kind of the dominant term here. So then you want this distance is going to be VR times dt. This is going to be the distance dy there, right? dy at r. And so this part is just v not dt, and then this part is the second part of that, right? So this is how we can get that. And here we know that this is going to be, again, let me write this with another color. This. So this is just u naught dt. Okay, we know this. Okay, so now let's calculate the average angular rotation about the z-axis. And the z-axis is just here, right? The axis. This is z-axis, okay. So it's going to be, let's say wz is, in time dt, it is going to be d alpha, which is clockwise. So d alpha minus d beta over 2, because this is going to be average of that, over dt, because we want to see what is the average rotation. So d alpha minus d beta, and d beta because it is, so d alpha, it is caused by partial v over partial x, and it is counterclockwise. So that is the direction of that, the sign of that is positive, and d beta, it is negative, the sign of it is negative, and it is caused by partial u over partial y. Okay, and its sign is negative because it is clockwise, it is rotating clockwise. So you can calculate it here. I didn't write it down, but this part is going to be, again, partial u over partial y, right, times dy. So it is caused by that. And again, this is dx, the whole thing, if I didn't write it down, and the whole thing is dy. Okay. So this is how you can get the average angular rotation about the z-axis. And so if we want to say what is d alpha, we can approximate it, because we can approximate it, we can assume it is pretty small because dt is small. So we can approximate it with tangent of d alpha and what is the tangent of d alpha? It is partial v over partial x at O dx dt over, so I'm just calculating this, right? This over this. So for this, now let's calculate this. What is the length of this this part? It's going to be u naught dt plus dx minus u naught dt, right? So this is going to be u naught dt. We add it from here to this dx, and then we also have to subtract this part. So it's going to be exactly just dx. So we have, and these dx's are going to cancel out. So we are going to have partial v over partial x at O times dt. So this is going to be d alpha. And similarly, we can get d beta. So d beta can approximate it with tangent of d beta, which is going to be partial u over partial y at O times dy dt over v naught dt plus dy minus v naught dt, which is going to be partial u over partial y at O times dt. So now let's see what is wz. So the wz, we define it as 1/2 dt d alpha minus d beta, which is going to be 1/2. These dt's are going to cancel if we just put them here, but I can put it down. So 1 over dt partial v over partial x dt minus partial u over partial y dt. So these dt's are going to cancel out. So we get 1/2 partial v partial x minus partial u partial y. So similar, this was for a 2D flow. So similarly, if you do this similarly for a 3D flow field, we have, this was only if the velocity gradients are in the x and y plane. What if they are also in other planes? So for a 3D flow field, wz is going to be similarly 1/2 wy, sorry, we got the w, which is wz means the rotation around z axis. Now let's see what is the rotation around the other axis. Is like, this was a rotation around z axis. This is called because this is this way, so this is wz. What if the rotation about the y-axis? That's called wy, and also around the x-axis is called wx. So let's see what are those. So wy similarly is going to be 1/2 partial u over partial z minus partial w over partial x. And the rotation around about the x-axis, wx, is going to be 1/2 partial w over partial y minus partial v over partial z. Okay, so the whole rotation vector around all axes is going to be 1/2 First one is around x-axis, so we want to just write this one, which is going to be partial w over partial y minus partial v over partial z I in the x-axis. Then we have the y-axis, which is going to be this one, minus partial u over partial, because I put minus, so I want to put it the other way, so it's going to be partial w over partial x minus partial u over partial z. This is j. And then the last component is going to be for k, which is in the z direction, so this is going to be partial v over partial x minus partial u over partial y in the k component of this. Okay. So the rotation vector is going to be this. It is going to be 1/2 of the determinant of this matrix. I, j, k, partial over partial x, partial over partial y, and partial over partial z, which is the grad, u, v, w. Right? So this is going to be the determinant of this matrix. Going to be the rotation vector, which is going to be what? Which is going to be 1/2 the cross product of grad and velocity vector. Right? So this is how we calculate the cross term by using this matrix, right? Determinant matrix. And what is this? The curl of velocity or grad cross v. Defined it here. It is vorticity. So it's 1/2 omega, which is vorticity. We know it as vorticity. So vorticity is just 2 times the rotation. This is very important formula. So the magnitude of vorticity is 2y the local rate of rotation of a fluid and is given by the curl of the velocity. Okay, so this is very important conclusion, because this shows what is vorticity. When we talk about curl of velocity or vorticity, it is just 2 times the local rate of rotation, the rigid body rotation of the fluid particles. So we typically define rotational flow and irrotational flow based on the vorticity. Okay, so for example, we say a rotational flow, we define it as follows: rotational flow. We define rotational flow, omega is curl of velocity. A rotational flow is a flow where the vorticity or curl of velocity is not zero. Is not zero every point in the flow. So this vorticity should be everywhere. And the fluid elements move and deform, but also rotate in a rotational flow. How about irrotational flow? So in irrotational flow, this vorticity vector, which is curl of velocity, is zero every point in the fluid, every point, and the fluid particles, or the fluid elements, let's say, move and deform, but do not rotate. So they don't rotate. Okay. So let me show this. What do we mean by rotation? By rotation, we mean rigid body rotation. It doesn't mean we can have some rotation in the large scale sense, but if the fluid particles are not rotating, the fluid elements are not rotating, it's not a rotational flow. It could be still an irrotational flow. So let me say, what do I mean by this? So let's say we have some vortex that is rotating the flow counterclockwise, and then in outer region let me see if I can just use this is easier. So in outer region we have something like this, and we want to see if the fluid particles, say if you have a fluid particle here, so in a rotational flow, this fluid particle, what happens to this in a rotational flow? This is going to have, we have going to a rigid body rotation. What do I mean by this? This means that this particle in this rotational flow will also rotate itself. So we have something like this here. And then here we have something like this. It is rotating itself too, right? And then here it will be like this. Here we have something like this. Here it's going to be this, as you see, it is also rotating itself. It's not just, so it is rotating both itself and also around another axis, right? So this is what we call rigid body rotation. It needs to have some rigid body rotation in order to have this rotational flow. But we can have this large scale rotation, but still do not have, but still have a irrotational flow. How it's possible? So let's say we have this vorticity, say for example in a bathtub. Okay. So we have this vorticity only in the core. And what happens is, say, if we put this fluid element here, and then if, say, we have an irrotational flow, so instead of a rotational flow, we have an irrotational flow, how it's going to move. Because it's a rotational flow, and in a rotational flow, we don't have any rigid body rotation, so it's going to move like this. It will not have any rotation around this axis. So it's going to be, here it's going to be like this. Then here, and here. So this is how it's going to rotate if we have an irrotational flow. So in a rotational flow, we have a rigid body rotation, but in a rotational flow, vorticity here is only in the core of this rotation. So we have a vorticity only in the core, but everywhere else, every other point, the vorticity is just zero. This vector, if you calculate partial, this is going to be zero here. This is not zero. And vorticity is going to be zero every other than the core. So what is this like? This is like actually a bathtub. So if you put something in the bathtub, it will not rotate around itself, and you will just see something like this. Okay, so this is actually a rotational flow. So in order for it to have a rotation, we have the rotational flow, we should have some rotation as well, so around its own axis, right? So we have here a rotation around its own axis as the flow moves this way. But here, as you see, as the flow moves this way, we don't have any rotation in the object itself. So this is the difference between rotational and irrotational flow and vorticity, and how the vorticity plays a role here. And we showed that here in this session that the vorticity is just 2 times the rotation vector. And also we defined rotational and irrotational flow based on the vorticity definition, and showed that we can have only a kind of a rotation, but because we don't have any rigid body rotation, the vorticity is going to be 0 everywhere here, like in a bathtub, except the core. And so we have an irrotational flow. So in the next lecture, I'm going to use these concepts and start about rotation in the inviscid world by introducing velocity potentials and stream functions. Thank you very much, everyone.